The way I see the purpose of this problem is testing out your toolkit of various equations, and that's essentially what they're asking you, just to look at all the little relationships you can find with one-dimensional oscillators. What we're going to do is we're going to start off with looking at pieces of information that were given to us. So it looks like the spring was first set up vertically, and I'm not going to draw that because it's a small part of the problem. And it says that the spring stretched 0.150 meters when a zero point 0.3 kilogram mass was attached to it. So when a force of mg, zero point 0.3 kilograms times 9.8 meters per second squared, was attached to the spring vertically, it stretched this much. Then the spring is set horizontally on a frictionless table, and that same zero point 0.3 mass is attached to it, and it's at equilibrium. Then lastly, it is stretched at 0.1 meters and then released from rest. So now we're going to answer questions A through G with this scenario in mind. The first one is, what is the spring constant and angular frequency omega? Well, the equation for spring constant is there. Well, first of all, there's many, but the one I'm seeing here is I'm seeing that the spring is stretched a certain amount when the force is applied to it. And that could directly give you the spring constant, which is essentially the stiffness. So I use the equation K, spring constant, is some force acting on the spring divided by how much it stretches from equilibrium. So this is basically came from F equals Kx, right? So now plugging in the fact that a force of 0.300 kilograms multiplied by 9.8 meters per second squared was applied to the spring, and it stretched 0.150 meters. So the spring constant ends up being 19.6 newtons per meters, and that's the final answer. Now, since you have K, we can go ahead and add that to our toolkit of things that we know from this problem, and then we can answer new problems from there. And luckily for us, the question goes from A to G using stuff that we know from previous parts. So for part B, we might have something from part A we need. For omega, what I'm seeing here is the relationship omega is the square root of the spring constant divided by m. And that's a relationship in the notes. Go look it up. We know what K is just from our analysis just now. It's 19.6 newtons per meters. And the mass attached to it is 0.300 kilograms. Plugging it into the calculator, you get 8.08 radians per second. And there's your answer to A. Now for B, they're asking you the amplitude of the horizontal oscillations. Well, when I wrote down the fact that it was stretched 0.1 meter and then released, if it's released from rest, you know that it's never going to go greater than 0.1 meters from equilibrium. So that means that the amplitude is going to be 0.1 meters. So that actually ends up being a very simple read the question kind of problem. So the amplitude is 0.100 meters, and we are done for part B. Now also push this paper up a little bit. For part C, they're asking the magnitude of the maximum velocity. So for this one, what we do have is we have velocity in general being to negative omega a sine omega t plus phi, some sort of initial condition phi. What we might have learned previously is that we know a sine function always oscillates from 1 to -1, 1 to -1. And for all time, that's the only range that this function can oscillate, -1 to 1 to -1 to 1, and so forth. So if you want a vmax, you are essentially saying this sine function is going to equal to 1. So this becomes vmax equals negative omega a multiplied by 1. We know what omega is. We know what A is. That's going to equal to omega right here is 8.08 radians per second. A is 0.1 meters. So the Vmax ends up being 6.53 meters per second. Units should work out because this is in radians per second and this is in meters. So radians, meters per second is your final unit. The thing about radians, though, is as it's kind of a pseudo unit. So it's not a physical unit. It's just some sort of dimensionless property or dimensionless, property of the sine function. So it ends up being a meters per second final unit. Now for D, the question asks, we're almost halfway there, the magnitude of the maximum acceleration of the mass. Again, you're going to go ahead and say A is equal to omega, negative omega squared, times A cosine of omega t plus phi. Again, cosine, just like sine, oscillates between 1, negative 1, 1, negative 1, and so forth. So if you want to get A max, you say that this entire function just becomes 1. That's the maximum it could ever become. So A max is equal to negative omega squared A times 1. Omega squared is just 8.08 squared. A is just 0.1. And cosine of function is 1. This eventually ends up being 6.53 meters per second squared. And oops, I am sorry, this is incorrect. Now that I've looked at it, my paper that I'm referencing does not kind of confuse me. This, of course, since omega is 8.08 and A is 0.1, this should actually be 0.808 meters per second. So my apologies for that mistake right there. So the answer to part C is 0.808 meters per second. And the acceleration is 6.53 meters per second squared. So apologize for that mistake. For E, we need the period and the frequency. Well, we actually could figure out the frequency because we know that omega is 2 pi f. So since we know omega, we know f. This ends up being 1.286 hertz. The period is simply 1 over f, and it's in units of seconds. And that ends up being, if you plug it into your calculator, 0.778 seconds. So those are the answers to frequency and period. Last two is F and G. So F, the displacement, X as a function of time. So they're asking for an equation now. We use the general formula for displacement versus time, and that is going to be X of t equaling to A cosine omega t plus phi. Now this phi is probably the only reason why I did a video instead of just putting it on another slide. So we know what A is. We know A is 0.100 meters. We know omega is 8.08 radians per second. And we know t is just a variable. How do we find phi? Well, here's what we know. We know that at time equals 0, x of t is equal to negative a. Because I say negative because it's compressed 0.1 meters from equilibrium. So compression generally indicates a negative. Okay, well, you know that this cosine has to oscillate between negative 1 and 1. So at that time equals 0, this cosine is only of argument phi because time is 0, so this whole term goes away. So this t naught becomes a cosine phi. Well, this is negative a. So if negative a is equal to a cosine phi must equal to negative 1. So that negative a can equal to a times negative 1. In order for cosine of phi to equal to -1, phi must equal to pi. Or negative pi or pi, it really doesn't matter. So it could be whatever you like it to be. I'd say anyone is totally okay in my book. So we can go ahead and say this final function is as follows. And I just went ahead and said plus phi. Okay. So again, because we're basically sleuthing here, we know x of 0 has to equal to -a when they say, you know, what the initial displacement is. So in order to find phi in the first place, you needed to know the initial displacement because you want t in the argument to be 0. Once that's the case, then you have t of 0 is equal to a cosine of phi by itself. Now, it's a lot easier to figure out what phi is if you somehow make this t equal to 0. If not, if you don't have t equals 0, you can still theoretically find what phi is. And we're going to get into more complicated problems involving phi later on. So anyway, again, we made t equals 0. That was the easiest way to do that. We knew the initial condition to be that the spring was compressed 0.1 meters. So that's a negative a compression at t equals 0. And so that means negative a is equal to a cosine phi. And that means that cosine phi had to be -1 to make this a negative a on the right-hand side. And that made phi have to be having to be pi. So it's a long list of procedure, but to be honest, all it is plugging in a value and just solving for phi. That's all it comes down to in reality. And lastly, they want you to find the the velocity at t equals 0.05 seconds. Trying to compress all of this into a little bit of space, we see that v of t is equal to negative omega a sine omega t plus phi. Now we know what phi is, we know what omega is, and we know what a is. So this is really easy. Plugging in t of 0.15 seconds, we're going to get 0.757 meters per second. And that is the answer to part G. Excuse the shadow, but here are all the parts.